Okay, hi everyone. We're going to be doing a quick explanation of the sbrk and brk system calls and how they're implemented and how they work for optimistic allocation. So first let's talk about the virtual memory layout of a process. And for this we'll be thinking about a layout of a process in a very simple kernel like WinCOS. And in this case, our kernel is going to be identity mapped in this lower region of memory here. This should be pretty standard. And we'll say that the rest of memory here can be dedicated to the process. Okay, here we have the code section. So this is all of the text that the process needs to execute. BSS and other constants, so initialized and uninitialized data section, and then heap. And initially the heap will be empty, so this will be a 0 length segment starting at the end of the initialized and uninitialized data here. And this heap will expand this direction outwards. And then finally we have the stack, and the stack will expand this way. So the entire idea behind sbrk and brk is we're going to have this value that we're going to call the break. So if we make our heap a little bit bigger, so let me redraw this here. This endpoint here of the heap is what we call the break. And the idea behind sbrk and brk is that they're just adjusting this value here. And the memory that is within this region here of the heap will need to be dynamically allocated and removed as the break is moved around. So first let's talk about what these two system calls do. First let's talk about sbrk. This system call takes an argument that is a value to either increase or decrease the break. So in this case, if the increase is 10, then it'll move the break forward by 10 bytes. And if it's negative 10, it'll move it back by 10 bytes. And the return value of this sbrk is actually just the break here, the address of this location. And similarly, the break system call, instead of taking increment, it actually takes a new desired address for the break point. So it takes the break and it also returns the break. So you can imagine that these two system calls are similar enough that you can implement them with just a single helper function. And that helper function is entirely in charge of just moving this breakpoint around for a single process. Now we haven't talked yet about this optimistic allocation part and what this does to affect how the heap is managed. A process could call sbrk with an increment of memory that it actually never ends up using. You might imagine that if you're reading input into a buffer and you don't know how many input characters you're going to read, you may need to over allocate the size of that buffer in order to fit everything in there. So let's zoom in a little bit into the heap, and I'm going to draw it as a large rectangle here. We've got our break here, and this heap region is going to be divided into a set of virtual pages, right? The idea behind optimistic allocation is that we're not going to initially map these pages to physical memory, but rather we're going to map them when they're used. So you can imagine the process will try and put things into this heap. Let's say it decides that it wants to use this page. From the kernel's perspective, what will happen is the process will try and write into some portion of memory. And since this virtual page is not mapped to a physical frame, you'll get a page fault. And so when this happens, the kernel can actually map this virtual page to a physical frame. And so now this page has a true mapping. And once this mapping is set up, then we can resume the process. And so over time, as the process uses parts of this heap, we'll end up mapping pages one by one. Although it doesn't necessarily have to be one by one. It could, for example, map 3 pages at a time whenever a page fault occurs, so that less trips to the kernel have to be made to map this memory. Okay, so what happens if we have some pages over here that have been used by the process? And so let's say we've used this one here. And the process calls sbrk in such a way that the break is reduced. So let's say the new break is here. In this case, on that sbrk call or brk call, we'll actually, at that point, we'll just deallocate all of the pages that have been mapped. So this specific mapping will be removed, and this page will no longer be, this virtual page will no longer be mapped to a physical frame.